27,000 light-years from where you're lying right now, there is a place where physics starts to break. It sits at the exact center of our galaxy, hidden behind 50,000 light-years of stars, gas, and dust so thick that no human eye will ever see it directly. We call it Sagittarius A star. For most of the last century, we believed we knew exactly what it was. A black hole. The biggest one in our galactic neighborhood, 4 million times heavier than our sun, compressed into a space smaller than the orbit of Mercury. That's the story you've probably heard before. Tonight, we're going to tell you a different one. Because in February 2026, a small group of physicists in Argentina published a paper that didn't try to prove Sagittarius A star is a black hole. They tried to prove it doesn't have to be, and when they ran the numbers, the universe didn't object. Their alternative model fit the data just as well, maybe even a little better. If they're right, the thing sitting at the heart of our galaxy isn't a black hole at all. It's something stranger. Something made of a kind of matter we've never directly seen, never directly touched, and can barely describe with the laws of physics we have. Something that doesn't just sit at the center of the Milky Way. It might stretch outward from there, quietly, invisibly, through every corner of the galaxy you can see in the night sky. You don't need to do anything right now except listen. Let your eyes close if they want to. We're going to take this slow, the way we always do, and walk all the way back to where this story begins. Back before black holes were even a serious idea. Back to a strange radio signal nobody could explain. In 1931, a young engineer named Carl Jansky was working for Bell Labs in New Jersey, trying to track down a source of static that kept interfering with transatlantic radio calls. He built an antenna that could rotate slowly on a turntable, something his colleagues nicknamed Jansky's merry-go-round, and pointed it at the sky almost as an afterthought, just to rule the heavens out as a suspect. What he found instead was a steady hiss of radio static that rose and fell on a strange schedule. Not a full 24-hour cycle, 23 hours and 56 minutes. A sidereal day. The time it takes the stars, not the sun, to return to the exact same position overhead. That tiny 4-minute difference told him something extraordinary. This static wasn't coming from a thunderstorm. It wasn't coming from the sun. It was coming from somewhere far beyond our solar system. And it was strongest in one particular direction, toward the constellation Sagittarius, toward the very center of our own galaxy. Jansky had just discovered radio astronomy without meaning to, but in 1931, there was no instrument sensitive enough, and no theoretical framework patient enough to ask what was actually producing that signal. Black holes weren't a real possibility yet. They existed only as strange, almost embarrassing solutions buried inside Einstein's equations, the kind of math problem most physicists quietly set aside, certain that nature would never actually do something so extreme. It would take more than 40 years before anyone pointed the right tools, with the right ideas in mind, back at that same patch of sky. In 1974, astronomers Bruce Balick and Robert Brown used a newly built radio interferometer in West Virginia and discovered that the signal coming from Sagittarius wasn't a spread-out cloud, and it wasn't a loose cluster of stars. It was a single, compact point of radio emission, smaller and stranger than anything else like it in the sky. Brown gave it the name we still use tonight, Sagittarius A star, with that little asterisk standing, in the dry humor of radio astronomers, for exciting. By then, the theoretical groundwork had finally caught up. Physicists like John Wheeler, Roger Penrose, and Stephen Hawking spent the 1960s proving, rigorously, that black holes weren't just a mathematical accident. Under the right conditions, Einstein's own equations didn't just allow them, they demanded them. So when astronomers found a compact, massive, completely invisible object sitting exactly where theory said something like a black hole should be, the pieces seemed to click into place almost too neatly. But seeming to fit isn't the same as proof. Through the 1980s, the case for a black hole at the center of our galaxy remained circumstantial, suggestive, but unconfirmed. The real breakthrough didn't arrive until the 1990s, when two competing research teams, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in the United States, pointed some of the most powerful telescopes ever built at that same dark patch of sky and began doing something almost absurdly patient. They tracked individual stars, one slow orbit at a time, year after year, as those stars swung around something they could never actually see. One particular star became the centerpiece of the entire story. Astronomers gave it the deeply unglamorous name S2. S2 completes a full orbit around Sagittarius A star in just under 16 years. For comparison, our own Sun takes more than 200 million years to complete a single orbit of the galaxy. At its closest approach, S2 is moving at roughly 24,000 kilometers per second, close to 8% of the speed of light, and somehow it doesn't get torn apart, and it doesn't get swallowed. It swings past whatever's waiting there in the dark and comes looping back around, again and again, like a comet that never quite falls in. From the exact shape and speed of an orbit like that, you can do something that sounds almost impossible. You can weigh an object you cannot see. Genzel's and Gez's teams independently calculated that whatever sits at the center of our galaxy weighs about 4.3 million times more than our Sun, and is somehow confined to a region smaller than the distance between the Sun and Mercury. Nothing we know of, other than a black hole, should be able to pack that much mass into a space that small without collapsing, or exploding, or simply not existing. In 2020, Genzel and Ghez were awarded the Nobel Prize in Physics, sharing the honor with Roger Penrose for the mathematical work he'd done decades earlier, proving that black holes were an unavoidable consequence of general relativity. To most of the world watching, it felt like the final word. Sagittarius A star was a black hole. Case closed. Except if you read the actual wording of that Nobel citation closely, it doesn't say, "for the discovery of a black hole." It says, "for the discovery of a supermassive compact object." That phrasing wasn't an accident, and it wasn't an oversight. It was the Nobel Committee being exact about something the scientists themselves already understood better than anyone. Every piece of evidence pointed toward a black hole, and a black hole remained, by a wide margin, the simplest explanation available. But nobody had actually proven it. Not in the way physics demands proof. They had only weighed something they could not see, and measured how small it had to be. What that something actually was, deep down, at its core, stayed an open question. The world simply stopped asking it. Here's the part of the story most documentaries skip over, because it complicates a tidy ending. We don't actually understand how an object like Sagittarius A star is supposed to form in the first place. That sounds strange to say out loud, because we do understand, very well, how smaller black holes come into being. When a massive star finally exhausts its nuclear fuel, the outward pressure that had been holding it up against its own gravity for millions of years disappears almost instantly. The core collapses. If the star started out massive enough, that collapse doesn't stop at a neutron star. It keeps going, past every point where matter can resist, all the way down, until what's left behind is a black hole. This process has been observed, modeled, and confirmed more times than almost any other phenomenon in astrophysics. We even have a rough head count. Astronomers estimate there could be as many as 1 billion black holes scattered quietly across the Milky Way, most of them only a few times heavier than our Sun, the leftover ashes of stars that burned out long before humans existed to notice. But stellar collapse has a ceiling, and that ceiling is nowhere close to where Sagittarius A star sits. No star, however massive, leaves behind a black hole anywhere near 4 million solar masses. There isn't a star big enough to make the jump. Even the most extreme stars ever detected top out somewhere around 200 solar masses before they tear themselves apart in a supernova. You cannot get from a couple hundred suns to 4.3 million suns simply by stacking dead stars on top of one another, one collapse at a time. The math refuses to connect. Astronomers have a quiet name for this gap. They call it the supermassive black hole formation problem. And it isn't a minor footnote tucked away in some obscure journal. It's one of the deepest open questions in modern astrophysics. We see objects like Sagittarius A star sitting at the centers of almost every large galaxy in the observable universe, including galaxies so distant and so old that their light left them less than 1 billion years after the Big Bang itself. And after decades of study, we still don't have one single, complete, agreed-upon story for how even one of them came to exist. There's a second problem layered on top of the first, and it's one we touched on briefly already, but it's worth sitting with properly here. A black hole, by its very definition, cannot be seen. Light that crosses its event horizon never comes back out to tell us anything, which means every single black hole humanity has ever claimed to detect, including this one, has been detected indirectly, through gravity, through the way it bends passing light, through the way stars and gas swing around something we are never permitted to look at directly. And that has a strange consequence. Every piece of evidence for Sagittarius A star being a black hole is, by the same logic, also consistent with it being something else entirely. Something with exactly the same mass, occupying exactly the same space, pulling on nearby stars with exactly the same gravitational strength, while not being a black hole at all. For most of the last 50 years, that possibility stayed almost entirely theoretical. A footnote physicists raised at conferences and then quietly set aside, because a black hole was simpler, more thoroughly worked out, and the available data never gave anyone a strong enough reason to look elsewhere. That changed, very quietly, in February 2026. Before we get to what changed in 2026, it's worth knowing that Sagittarius A star has never had a completely uncontested identity. Almost as soon as black holes became a respectable scientific theory, other physicists started quietly asking a different question. What if there's something else out there capable of doing everything a black hole does, without actually being one? One of the earliest serious contenders was the boson star, a hypothetical object built not from ordinary matter like protons and electrons, but from an entirely different family of particles called bosons. Bosons behave strangely under quantum mechanics, in a way that ordinary matter never does. They're sociable. Under the right conditions, an enormous number of them can pile into the exact same quantum state at once, essentially merging into a single, unified wave of matter, rather than remaining countless separate particles. In theory, enough bosons drawn together by gravity could form an object massive and compact enough to mimic a black hole's pull on nearby stars, without ever forming the one true signature of a black hole. An event horizon, that final one-way boundary nothing can cross back over. No one has ever observed a boson star. We aren't even certain the right kind of boson exists in nature to build one. But more than half a century after the idea was first proposed, the mathematics behind it has still never been ruled out. A second, even stranger idea is the gravistar, short for gravitational vacuum star. And it's the kind of concept that becomes almost unsettling the longer you sit with it. Instead of a dying star's core collapsing all the way down into an infinitely dense point, the proposal is that the collapse triggers something closer to a phase transition, the same basic kind of process that turns liquid water into solid ice. Somewhere deep in that collapse, ordinary matter is theorized to convert into a strange, ultra-dense shell wrapped around a bubble of vacuum energy, unlike anything else in the universe. From the outside, a gravistar would look almost indistinguishable from a black hole. Same overwhelming gravity, same general size and shape, but with no true singularity hidden inside, and no genuine event horizon trapping anything inside it forever. Neither of these two ideas ever gained much traction among working astronomers, and the reason is fairly simple. As decades of precise data accumulated on the orbits of S2 and the other stars circling Sagittarius A star, both the boson star and the gravistar models struggled to reproduce the fine details with the same easy precision that a plain, ordinary black hole could. They weren't disproven outright. They were simply outcompeted, quietly, pushed further and further toward the margins of the field as the black hole explanation kept winning, comparison after comparison. But the fact that they persisted in the scientific literature at all, even at those margins, even after losing comparison after comparison, tells you something worth remembering. The black hole explanation has never been the only mathematically possible one sitting on the table. It has simply been the best one available for the longest stretch of time, given the data anyone had to test it against. And the moment a genuinely new model comes along that fits that same data just as well, or even slightly better, that's exactly the moment the conversation reopens. That's exactly what happened next. In February 2026, a paper appeared in the monthly notices of the Royal Astronomical Society, led by physicist Valentina Crespi at the Institute of Astrophysics of La Plata in Buenos Aires, alongside her colleague Carlos Arguelles and a wider international team of collaborators. Their question wasn't whether Sagittarius A star could be a black hole. It was whether it had to be. Their proposal was this. Instead of a singularity wrapped tightly inside an event horizon, the object at the center of our galaxy could be an extraordinarily dense, stable core made entirely out of dark matter. Not ordinary matter compressed past the point of no return, the way a black hole forms. An entirely different category of stuff altogether, held together by entirely different physics, stable in a way a black hole can never be. To test an idea like that, you can't just argue for it. You have to build it, mathematically, piece by piece, and then throw the same evidence at it that decades of black hole research had already collected. So that's exactly what Crespi's team did. They constructed a full model of a dense dark matter core and compared its predictions directly against the real orbital data of S2, alongside 5 of the strange, gas cloud-like objects known as G objects, first identified in the early 2000s. G objects are genuinely bizarre. Gravitationally, they behave like compact stars, swinging through tight, fast orbits close to the galactic center. Visually, though, they stretch, distort, and change shape as they make their closest approach, almost like a comet's tail, being slowly shredded by overwhelming tidal forces. Whatever model wins this debate doesn't just need to explain S2's clean, well-mapped orbit. It needs to explain the messy, shape-shifting behavior of the G objects too, in just as much detail. When Crespi's team ran the comparison, the result wasn't subtle, and it wasn't ambiguous either. Their dark matter core model reproduce the orbits of S2 and all 5G objects, with less than a 1% difference compared to the standard black hole model. In practical terms, that means the orbital data we currently have, gathered over more than 3 decades of careful observation, simply cannot tell the two models apart. A black hole and a sufficiently dense dark matter core would tug on those same stars in essentially identical ways, curve their paths through essentially identical geometry, and leave behind essentially identical fingerprints in the data. On its own, that result would already be a meaningful contribution to the field, a serious challenge worth taking seriously. But Cresby and her collaborators went one step further, and this is the point where the story stops being just about one unusual object at the center of our own galaxy and starts brushing up against one of the biggest unanswered questions in all of physics. To understand why Cresby's model matters so much, you need the other half of this story. You need to understand dark matter itself. In the 1930s, around the same time Carl Jansky was puzzling over his strange radio static, a Swiss-American astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster. He measured how fast individual galaxies inside the cluster were moving relative to one another, and the numbers simply didn't add up. Some of them were moving at more than 2,000 kilometers per second, fast enough that, based purely on the visible mass of the cluster, gravity alone should never have been strong enough to hold the whole thing together. By every calculation Zwicky could make, the Coma Cluster should have flown apart millions of years ago, scattered into empty space. It hadn't. So either gravity worked differently than Einstein and Newton said it did, or there was a vast amount of additional mass hiding somewhere in that cluster. Mass that simply wasn't shining the way ordinary stars do. Zwicky called it Dunkel Materia, dark matter. The name stuck, even as almost everything else about it remained a complete mystery. Decades later, an American astronomer named Vera Rubin found the same unsettling pattern much closer to home, studying how fast stars orbit within individual galaxies, including our own. Stars far out in a galaxy's spiral arms, way beyond the crowded central regions, were moving just as fast as stars much closer in, which shouldn't happen if the only mass present was the visible matter locked up in stars and gas. Something invisible had to be providing extra gravitational pull, especially out at the edges, holding the whole structure together like a scaffold nobody could see. Today, astronomers think that invisible scaffold surrounds our entire galaxy in something called a dark matter halo, an enormous, roughly spherical cloud of unidentified material, far larger than the visible disk of stars and dust we usually picture when we imagine the Milky Way, stretching outward for hundreds of thousands of light years in every direction. Current estimates suggest dark matter makes up around 85% of all the matter in the entire universe. Ordinary matter, the stars, the planets, the gas, every object you've ever touched in your life, including your own body, is the rare exception, not the rule. And yet, despite outnumbering ordinary matter roughly 5 to 1, dark matter has never once been directly detected. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. Every single thing we know about it comes from watching how it tugs on things we actually can see. The exact same indirect approach astronomers have always used to study black holes. We know dark matter is out there, the same way you might know someone has walked quietly through a dark room, simply because you heard their footsteps, without ever once seeing their face. Physicists have spent close to a century now hunting for what dark matter actually is, deep down, at the particle level. The leading suspects carry names like WIMPs, short for weakly interacting massive particles, and axions, both hypothetical particle types that could explain everything we observe gravitationally while remaining almost completely invisible to every detector humans have ever built. In November 2025, one research team thought they might have spotted a faint signature consistent with WIMPs quietly annihilating each other, buried in old archival data from the Fermi Gamma Ray Space Telescope. It was tantalizing. It was also far from conclusive, and the question of what dark matter actually is remained, just as it always had, wide open. This is the exact mystery that Cresby's team walked straight into when they turned their attention to the center of our galaxy. And the answer they reached for had been sitting quietly in the scientific literature for more than 50 years, waiting for someone to take it seriously. In 1969, two physicists, Remo Ruffini and Silvano Bonazzola, proposed that dark matter might not be made of some exotic new particle type at all, but of a fermion, the same basic category of particle that governs ordinary matter, like electrons and quarks. They called the hypothetical dark version a dark fermion, and for almost half a century, almost nobody paid the idea much attention. To understand why this matters, you need to understand one of the strangest, quietest rules in all of physics, something called the Pauli exclusion principle. It states in essence that no two identical fermions can ever occupy the exact same quantum state at the exact same time, the same location, the same energy, the same spin, all at once. It sounds abstract, almost academic, but it has an effect you've experienced every single second of your entire life, whether you ever noticed it or not. It's the reason you can't push your hand through a solid table. The electrons in your hand and the electrons in the table simply refuse to overlap, refuse to occupy the same space at the same time. And that quiet refusal is solid enough, stubborn enough, to hold up the full weight of your body. Without the Pauli exclusion principle, matter as we know it wouldn't hold its shape at all. It would simply collapse in on itself. That same stubborn refusal is also what eventually halts the collapse of a dying star, at least up to a certain point. When a star's core collapses, its electrons get crushed closer and closer together until the Pauli exclusion principle pushes back hard enough to stop the collapse entirely, leaving behind what's called a white dwarf, a star's leftover core, now held up by nothing but that one quantum rule. Push even harder, pack in even more mass than a white dwarf can bear, and you can crush past that limit too, converting electrons and protons into neutrons, which then resist collapse through the very same principle, leaving behind a neutron star, one of the densest objects known to exist, an object so tightly packed that a single teaspoon of its material would weigh roughly as much as a mountain back here on Earth. Push past even that limit, add enough mass on top of a neutron star, and there's no known force left in the universe to resist any further. The object collapses all the way down, with nothing left to stop it, into a black hole. Cresby's model proposes that dark fermions behave the same stubborn way. They obey the Pauli exclusion principle too. They resist being squeezed down into a single point, the same way the electrons in your hand resist passing through a table. Given enough dark fermions, drawn together slowly by gravity over billions of years, they could build up enormous internal pressure, enough to form an object every bit as massive and as compact as a supermassive black hole, without ever crossing that final line into total collapse. No singularity hiding at the center, no event horizon sealing anything off forever. just an almost unbelievably dense, stable sphere of matter, held up by the exact same quiet, quantum stubbornness that keeps your hand from passing through solid objects, scaled up to a size 4 million times heavier than our Sun. And dark fermions wouldn't stay neatly confined to that tiny central region either, because they only interact with the rest of the universe through gravity, never through light, never through any other known force. The model predicts they would naturally spread outward from that dense core into the much larger, far more diffuse halo of dark matter already thought to surround the entire galaxy. Not two separate things sitting near each other by coincidence. One single continuous structure, dense and compact right at the center, gradually thinning out the further you travel from it, the way fog sits thickest, exactly where it forms, and fades quietly the further it drifts from that source. This is the part of the idea that makes physicists sit up a little straighter. Every other proposal for what Sagittarius A star might be treats the object at the galactic center and the dark matter halo surrounding the galaxy as two separate mysteries that simply happen to coexist in the same general neighborhood. Cresby's model is the only one on the table that suggests they might be the exact same thing, observed at two completely different scales. One of the deepest open mysteries about our own galaxy's core, and one of the deepest open mysteries about the universe as a whole, possibly, just possibly, turning out to share the very same answer. A theory this elegant means very little if it can't survive contact with real observational data. So let's walk through the evidence, piece by piece, the same patient way the researchers themselves had to. The first piece comes from the European Space Agency's Gaia mission, a spacecraft launched with one extraordinarily patient goal in mind: to measure the precise position and motion of roughly 1 billion stars across our galaxy, charting how each one moves as it slowly orbits the galactic center over the course of a human lifetime, and far beyond it. When Gaia's data was published in 2022, it revealed something nobody had fully expected to find: a phenomenon astronomers call a Keplerian decline, a gradual slowing in the rotation speed of stars way out in the galaxy's outer arms, far from the crowded center. It's a subtle effect, easy to miss if you aren't looking carefully, but a deeply important one, because most existing dark matter models struggle to reproduce it cleanly. The fermionic dark matter model, though, makes a very specific prediction here. Because dark fermions resist infinite compression, thanks to that same Pauli exclusion principle, the halo they would form should have an unusually sharp, well-defined outer edge, rather than fading out gradually and indefinitely, the way most other dark matter candidates predict. A sharper-edged halo naturally produces exactly the kind of fall-off in rotation speed that Gaia detected, almost as if the prediction had been written before the observation, rather than after it. Gaia wasn't just mapping a billion individual points of light. It was, without anyone quite intending it that way, tracing the outer boundary of something we still cannot see directly. The second piece comes from an image you've almost certainly seen before, even if you never knew its full story. In 2022, the Event Horizon Telescope released its now famous picture of Sagittarius A star, a softly glowing ring of light wrapped around a dark, empty center, instantly described around the world as the first direct image of a black hole's shadow. What the image actually shows, in more careful terms, is superheated gas swirling so close to the galactic center that the extreme gravity there bends its light into that characteristic ring shape, with a dark void sitting at the middle, where light gets either trapped entirely or bent so sharply it never reaches our line of sight. It's a stunning, hard-won piece of science, the product of telescopes spread across the entire planet, working together as one. It is also, importantly, not exclusive to black holes. In 2024, Arguelles and his collaborators showed mathematically that a sufficiently dense fermionic dark matter core would bend light almost exactly as strongly, producing a near-identical dark shadow surrounded by a near-identical bright ring, indistinguishable from the black hole image, given the instruments we currently have available. The very picture that convinced most of the world's Sagittarius A star was a black hole turns out to be just as consistent with it not being one at all. The third piece takes us much further away and much further back in time. The James Webb Space Telescope has given astronomers the ability to look at galaxies so distant that their light has been traveling toward us for almost the entire history of the universe. Galaxies as they existed less than 1 billion years after the Big Bang itself. Buried inside some of these ancient, faraway galaxies, astronomers have found peculiar, compact objects, nicknamed little red dots, extraordinarily massive, extraordinarily small, and extraordinarily early in cosmic history. Some appear to already contain the equivalent of hundreds of millions, even billions, of solar masses concentrated into a tiny region, at a point in the universe's life when there simply shouldn't have been enough time for an object that large to grow through any process we currently understand. They've sparked hundreds of scientific papers and almost as many competing explanations in the few short years since their discovery. A fermionic dark matter core sidesteps the entire timing problem rather elegantly. In the extraordinarily dense, chaotic conditions of the very early universe, dark fermions could have clumped together directly under their own gravity, forming massive compact cores almost immediately, without first needing a star to be born, live out its life, and eventually die. If that's true, it would explain why the universe seems to have built monstrously massive objects at the centers of galaxies far earlier than it should ever have been able to. The fourth piece brings us back to the orbit of S2 itself, the very same star whose 16-year loop helped earn a Nobel Prize. Cresby's team didn't stop at checking whether their model could reproduce S2's basic, well-mapped orbit. They went further and checked whether it could match the small, strange, shape-shifting behavior of the G objects too, the gas cloud-like bodies that stretch and distort as they swing close to the galactic core. Both the black hole model and the dark matter core model passed that more demanding test with nearly identical precision, leaving almost no daylight between them in terms of accuracy. 4 separate pieces of evidence, 4 completely different instruments, built decades apart, by entirely different teams, for entirely different original purposes. And every single one of them turns out to be just as comfortable with a dense ball of ancient dark matter sitting at the center of our galaxy as it is with a black hole. If you've been listening closely, you might already be asking the obvious question. If the evidence fits both models this well, how would we ever know for certain which one is actually true? There is one answer, and it lies in something extraordinarily subtle, even by the standards of everything we've covered tonight. It's called the photon ring. A true black hole has an event horizon, a boundary so steep, so unforgiving, That light passing close enough can be forced to circle the black hole multiple times, looping around and around in tighter and tighter spirals, before either finally escaping outward or vanishing forever beyond the horizon. Those repeated loops leave behind a faint, distinct signature in the light astronomers eventually receive, an extremely thin, extremely precise ring of light, nested just inside the brighter, broader ring we already see in images like the one captured by the Event Horizon Telescope. A dark matter core, by contrast, has no event horizon at all, none whatsoever. There's no true point of no return hidden inside it, no boundary that traps light permanently. Light passing close to a dark matter core gets bent by its gravity, sometimes quite dramatically, almost as dramatically as around a black hole. But it ultimately escapes, bent, redirected, sent off in a new direction, but never trapped, and never forced into the repeated spiraling loops that create a genuine photon ring. If Cresby's model turns out to be correct, that telltale ring, the one a true black hole should always leave behind, simply wouldn't be there to find. The problem is that actually detecting a photon ring requires a level of resolution that borders on the unimaginable, finer detail than even the Event Horizon Telescope can currently achieve. NASA's proposed Black Hole Explorer mission aims to change that by linking a brand new space-based radio telescope directly with a next-generation Event Horizon Telescope array, effectively creating one virtual telescope larger than the planet Earth itself. It's an extraordinary engineering ambition, the kind that pushes against the limits of what's currently possible, and it could realistically be decades before it's fully up and running. In the meantime, a smaller, steadily improving instrument is already chipping away quietly at the problem. The gravity interferometer, based at the Very Large Telescope facility high in the mountains of Chile, has been carefully tracking a subtle wobble in S2's orbit, a phenomenon called pericenter precession, small shifts in the exact shape and orientation of its 16-year loop with every single pass it makes. The direction and magnitude of that wobble could, eventually, with enough patience and enough data, help rule certain models in and certain models out for good. And on an entirely different front altogether, particle physicists are trying a more direct approach, attempting to catch dark fermions themselves rather than inferring their presence from millions of light-years away. Experiments like the neon detector in South Korea are searching for the faintest possible signature of a dark particle colliding with an ordinary electron, a flicker of energy so small it sits right at the very edge of what our most sensitive instruments can register at all. If something like that is ever detected, even once, it wouldn't just answer the question of what's sitting at the center of our galaxy. It would tell us, for the very first time in the history of science, what 85% of all the matter in the universe is actually made of. So let's sit with this for a moment, slowly, the way we like to do here. If Cresby and her collaborators turn out to be right, the object at the center of our galaxy isn't a doorway to nowhere, the way a black hole is so often described in books and documentaries. It's something closer to ancient, a dense, stable knot of the same invisible material that makes up most of the universe around us, gathered together, not over millions of years the way a black hole slowly grows, but possibly within the first sliver of cosmic time, long before our sun existed, long before our planet existed, long before anything resembling us was even a possibility written into the laws of physics. And it wouldn't be sitting there alone, isolated at the center, the way a black hole sits in stark, total isolation from everything around it. It would be continuous, connected, the very same kind of matter, just more spread out, drifting quietly through every part of the galaxy you've ever looked up at on a clear night, through the space between the stars in the Big Dipper, through the dark, empty-looking gaps between constellations, present, in some small but real amount, in every single direction you've ever pointed a telescope. Your entire life, without ever once realizing what might already be filling the space around whatever you were actually looking for. It's a strange thing to sit with. We've always told the story of black holes as the universe's full stops, places where physics simply ends, where nothing that falls in ever comes back, where the story of anything that crosses that boundary is permanently erased from the universe. A dark matter core offers something almost the opposite. Not an ending, a presence, something old, something vast, something that has been quietly there since long before we had names for galaxies, or constellations, or even numbers to count the stars with, doing nothing, watching nothing, because it has no eyes and doesn't need any, just existing, unbothered, at the exact center of everything we call home. We don't know yet, not for certain, which version of this story is actually true. The honest answer, the one Cresby's own team is careful to give in their published work, is that the black hole explanation is still considered the most likely one by a wide margin. Nothing here has overturned that consensus, and nothing here is claiming to. What has changed is something quieter, and in its own way, a little more unsettling than a clean answer would have been. We now know, with real confidence, that we cannot rule the other possibility out. Not with the data we currently have in hand, not with the instruments we've managed to build so far. Sometimes the most honest thing science can offer is simply, we don't know yet. And somehow, that sentence has never once stopped being one of the most fascinating things about the universe we live in. 27,000 light years away, something is still sitting exactly where it's always been, doing exactly what it's always done, completely indifferent to whether we ever figure out the right word for it. Maybe it's a black hole, just as the textbooks have said for decades. Maybe it's something older and stranger, a quiet, ancient gathering of the very same material that holds the rest of the universe together, hiding in plain sight at the center of the only galaxy we will ever call home. Either way, it isn't going anywhere. It will still be there tomorrow night, and the night after that, turning slowly at the center of everything, long after you've drifted off. Sleep well,